Okay, there are oftentimes energy changes that are associated with those different physical and chemical changes that we talked about. When water evaporates, there is an energy change occurring. When water evaporates from your skin, what do you feel? As that sweat evaporates, you feel cooler, right? Why is that? Because it's absorbing energy from your skin. The idea behind a swamp cooler, where you have this mat of straw-looking stuff that water comes over and you blow air through it and it evaporates and it makes the air cool. It's because the evaporation of the water absorbs energy from the air, making the air cooler. When natural gas burns, if you have a gas stove at home and you light it, is there energy associated with that? Yes. Yeah, that burner gets hot, right? That's the only reason we burn natural gas in the stove, is to make the silly thing hot. It's releasing a lot of energy. Those are physical change of water evaporating involves energy, and the chemical change of natural gas burning involves energy. So energy gets released during a chemical reaction, just like energy is released when a weight falls to the ground. So here we've got a 10-kilogram weight on top of this building, and somebody pushes it. It's teetering on the edge here. It's unstable. It has high potential energy. As it comes down, that potential energy is converted into kinetic energy, and when it hits the cement down here, the kinetic energy is converted into heat energy. In a chemical reaction, we have potential chemical energy being converted into light or heat energy. So just like the weight on top of the building, have you ever seen something on the sidewalk just spontaneously float up and perch on top of a building? Not a bird, just like a box. You ever see a box fall up and land on the building? No. Can you imagine a box falling off the top of a building? Sure, that could happen very easily. Systems go from high potential energy to low potential energy. A system with high chemical energy, like gasoline, will burn explosively and produce things with lower chemical energy. So we see that this energy is a driving force and helps us to predict what's going to happen. TNT, trinitrotoluene, that's a tongue twister, tends to undergo rapid chemical changes. That's why it's in dynamite. It's explosive. It releases a tremendous amount of that stored potential energy when the chemical reaction occurs. That's an example of a substance that has high concentrated potential energy. So we can look at these chemical reactions and identify, are they absorbing energy or are they releasing energy? So an exothermic reaction, therm has to do with energy, usually heat. Exo means on the outside or going outside. We have an exit sign. When you exit, you go out. Exothermic means the energy is going out of the system. So in an exothermic reaction, the reactants start at high energy and they end up at low energy. The energy that they had initially is released in some form. You can also have an endothermic reaction. Endo is a prefix that means going in. It's a little bit like the word into. Endo, into. Energy going into. So the endothermic reaction, the reactants have low energy and they absorb the energy from their surroundings and make products that have higher energy. Exothermic reactions are probably more common because this is more natural for things to go from a high energy state to a low energy state. Endothermic reactions occurring by themselves are not that common, but you can couple them with other things and get them to happen when you want to. So let's identify these changes as exothermic or endothermic. Water freezing into ice. So the first loud murmur was endothermic, and then I heard someone say exothermic. Okay, let's think about this. Water freezing into ice. That one is maybe a little hard to think about. It's easier to think of the opposite. Ice melting into water. What do you have to do to get ice to melt? Do you take heat out of it or put heat in? You put heat into it. Putting heat into it would be endothermic. If melting is endothermic, the opposite, freezing, has to be exothermic. Most of you, yeah, you win. You, the one voice in the wilderness. Most of you have a freezer at home, right? The freezer is a little box with this convenient door on it, and there's like ice cream and yummy stuff in there, right? How is it cold in there? Do you ever think about that? Oh, well, it's a machine. It makes it cold. It uses pressure of gas, expanding, contracting, expanding, contracting. It's essentially sucking energy out of the inside of your freezer. In order to freeze water into ice, you have to pull the energy out. That's something that's hard to visualize because it's really hard to see how that's happening. It's much easier to visualize putting energy into something. You put the ice cubes in a pan on the stove and you turn the burner on. You feel the heat. You know the heat is going into the pan. You watch the ice cubes melt. So melting is endothermic. Water freezing is exothermic. So this is exothermic. How about natural gas burning? Exo. Think about natural gas burning. Is energy coming off of that? Yeah, it's releasing energy. That's also exothermic. So you can't just think about, well, is it hot or is it cold? Cold things are endo, hot things are exo. No. It's how is energy moving? That's how you identify exothermic versus endothermic.